On the 8th of May 2026, seismometers picked up a swarm of earthquakes underneath a stretch of ocean that barely anyone on the planet had ever thought about before. No one was watching it because there was almost nothing to watch. This patch of the Bismarck Sea, north of Papua New Guinea, was one of the least mapped pieces of ocean floor on Earth, an area where scientists genuinely knew less about the seabed than they know about the surface of Mars. And then, within hours of that earthquake swarm, satellites orbiting hundreds of kilometers overhead caught something that made volcanologists sit up straight. Steam. White, dense, churning steam, rising directly out of open ocean where no volcano was known to exist. Ash climbing several kilometers into the sky. The water itself changing color, turning a strange greenish milky tone across an area so large it would eventually be measured in the thousands of square kilometers. Something enormous had woken up beneath the waves, and almost nobody had any real idea what it actually was. By the end of this, you're going to understand exactly what has been happening under the Bismarck Sea for the last 3 months, why scientists are calling it one of the most extraordinary natural events of the decade, why there's a very real chance it could give birth to a brand new island, and why this same stretch of ocean has already produced one of the deadliest volcanic disasters in modern history, one most people have never even heard of. We're going to walk through the timeline of how this eruption unfolded, break down the almost unbelievably complicated geology sitting underneath this part of the planet, look at the human communities already being affected right now, and then get into the honest, sober question hanging over all of it. Is this a strange but contained curiosity, or is it a warning sign for something far larger? Stick with me through this one, because there's a lot to unpack. And if you find this as fascinating as I do, drop a comment and let me know your thoughts as we go, because I read every single one. Let's rewind to before any of this made headlines, because the story doesn't actually start on May 8th. It starts weeks earlier, in near total silence. On March 31st, 2026, a seismic station on nearby Manus Island picked up an unusual burst of tremors coming from far out at sea. Nobody paid much attention. Earthquakes happen constantly in this part of the world. Then, on April 25th, a second distinct swarm of seismic activity hit the exact same patch of ocean. 2 unrelated bursts of shaking, 5 weeks apart, both centered on a stretch of seafloor with no known volcanic feature attached to it. In hindsight, those 2 swarms were the pressure building. They were the warning nobody was positioned to read, because there was no monitoring equipment out there, no buoys, no seafloor sensors, nothing but distant seismic stations picking up faint signals from 100 kilometers away. Then came May 8th. At just after 1 in the morning, UTC, a new swarm of earthquakes began. This time it didn't taper off, it built. Within hours, the first satellite passes started catching plumes. By May 9th, the eruption was undeniable, an actual moving, breathing volcanic event unfolding in real time on satellite imagery, and scientists at NASA's Earth Observatory openly admitted they were confronting a situation with almost no reference points. Nobody had detailed maps of the seafloor. Nobody knew for certain which specific feature was erupting, what depth the vent originally sat at, or when this particular spot last did anything like this. The best working theory placed the new activity along something researchers began informally calling Titan Ridge, roughly 16 kilometers southeast of the site of a much smaller, largely unnoticed submarine eruption back in January of 1972. That 1972 event had only been detected through acoustic signals picked up by underwater hydrophones as far away as Wake Island and Midway Atoll in the middle of the Pacific, proof that even small ruptures out here send shockwaves rippling across entire ocean basins. Within days, the scale of what was happening became impossible to ignore. Sentinel-2 satellite passes showed a discolored patch of ocean water spreading out from the eruption site, eventually covering an area estimated at roughly 2,700 square kilometers. Try to picture that for a second. That's not a localized disturbance around a single vent. That is an area of ocean larger than some entire countries, tinted yellow and green from sulfur compounds and dissolved minerals being dragged up from deep inside the earth and released directly into seawater. At the same time, something else started showing up in the imagery that made this event genuinely unusual even by volcanic standards. Floating pumice, and not just a light dusting of it. By the middle of May, satellite analysts were tracking a raft of pumice stretching across roughly 70 square kilometers, an area larger than the island of Manhattan, just floating there on the surface of the Bismarck Sea, drifting with the currents, like a strange gray continent that hadn't existed 2 weeks earlier. It's worth pausing on just how strange it is that an event of this size could stay hidden until the exact moment it broke the surface. This part of the Bismarck Sea sits roughly 80 miles southeast of Manus Island in water that older bathymetric charts placed somewhere between 500 and 800 meters deep across the wider eruption zone, with the summit of what would later be called Titan Ridge sitting more than 400 meters below the surface before any of this began. That's deep enough that nothing about the seafloor there had ever been flagged as a hazard, deep enough that no shipping lane avoided it, deep enough that it simply wasn't on anyone's list of things to watch. Compare that to how a land volcano works, where decades of smoke, sulfur smell, and slow deformation of the ground usually give some kind of warning long before an actual eruption. Out here, there was none of that. There was only silence, then 2 isolated earthquake swarms 5 weeks apart that barely registered outside of specialist seismology circles, and then, essentially without warning, an eruption large enough to be tracked from space. Simon Karn, a volcanologist at Michigan Technological University, who has spent years tracking eruptions from orbit, looked at the thermal data coming off this site and drew a conclusion that reframed the entire story. The heat signatures were too intense, too persistent, and too close to the surface for a vent sitting several hundred meters underwater, the way the old, sparse bathymetric charts suggested. His read on it was straightforward. There had to be an enormous volume of extremely hot material sitting much closer to the ocean surface than anyone had assumed, which meant either the eruption itself was reshaping the seafloor at incredible speed, building up a new volcanic platform layer by layer, or the existing maps of this stretch of ocean were simply wrong from the start. Possibly both. And this is really the detail that should stop you in your tracks. In 2026, with satellites that can resolve individual houses from orbit, with ocean monitoring networks stretched across the globe, there is still a piece of the Pacific close enough to a populated island chain to threaten it, and scientists are learning what it looks like for the very first time, live as it happens. Now, let's talk about why this location is capable of producing something like this at all, because the geology underneath the Bismarck Sea is genuinely one of the most tangled, chaotic corners of plate tectonics on the entire planet. Most people, when they picture tectonic plates, picture a handful of giant continental slabs grinding against each other in slow motion. That mental picture completely falls apart once you look at this region. The Bismarck Sea sits at the collision point of several small tectonic plates and microplates all shoving against each other at once, a genuine jigsaw puzzle of crust squeezed between the much larger Pacific plate and the Australian plate. Titan Ridge itself sits right on the northern edge of what's called the South Bismarck Plate, and more specifically, right at the junction of 2 very different kinds of tectonic boundary. On one side, you've got the Willamette Transform Fault, a boundary where crust is sliding sideways past itself, similar in principle to California's San Andreas Fault, just underwater and far less studied. On the other side, you've got an active back arc spreading ridge, a zone where the seafloor is actively being pulled apart, and new crust is being generated as magma wells up to fill the gap. When you put those 2 mechanisms right next to each other, sliding faults tearing sideways and spreading ridges pulling apart, you create exactly the kind of weak, fractured, magma-friendly pathway that lets deep material punch upward toward the surface far more easily than it normally could. To put that in perspective, most volcanoes on Earth sit above a single, relatively straightforward type of tectonic setting. Either a subduction zone, where one plate dives beneath another, or a hotspot where a stationary plume of heat burns through the crust above it, or a spreading ridge pulling gently apart. Titan Ridge sits at the overlap of 2 completely different mechanisms operating on the same small patch of crust simultaneously, which is part of why researchers studying the region have described the Bismarck Sea's seafloor as riddled with rifts, scarps, and pockets of active subduction, all within a remarkably tight geographic area. It is, structurally speaking, one of the most fractured and unstable stretches of ocean floor anywhere on the planet, and that instability is precisely the mechanism that allowed something this large to build up in near total secrecy. This is precisely why this eruption behaved the way it did, and it's worth understanding the actual physics of a submarine eruption because it's genuinely different from anything happening on land. When magma erupts on the surface, it interacts with air, and the result, however violent, follows fairly predictable patterns. When magma erupts underwater, especially in relatively shallow water, like the several hundred meters depth estimated at Titan Ridge before this event, you get a much more volatile interaction. Superheated molten rock meets seawater directly, and that contact triggers rapid, often explosive fragmentation, flash boiling enormous volumes of water into steam almost instantly. That's what produces the towering steam plumes satellites were photographing from orbit. It's also what produces pumice on this scale, because the violent fragmentation process shreds cooling lava into a foamy, gas-filled rock riddled with so many air pockets that it floats, sometimes for months, sometimes for years, drifting wherever ocean currents choose to carry it. If you want a comparison point for just how dangerous this kind of shallow submarine eruption can become, you don't have to look far. In January of 2022, the Hunga Tonga Hunga Ha'apai volcano in the South Pacific erupted in a way that stunned atmospheric scientists worldwide, sending a plume soaring more than 50 kilometers into the atmosphere, triggering tsunami waves that crossed entire ocean basins and generating an atmospheric shock wave that circled the globe multiple times, registered on barometers as far away as the United Kingdom. That eruption became so explosive specifically because the vent sat at a depth where seawater and magma could interact with maximum violence, not so deep that the water pressure suppressed the explosion, not so shallow that it simply broke the surface calmly. Titan Ridge, sitting in that same general depth range before this eruption began reshaping it, is uncomfortably positioned in a similar danger zone. Nobody is saying this event is destined to replicate Hunga Tonga, but the fact that serious scientists are even drawing that comparison should tell you how seriously this needs to be taken. And it's exactly why aviation authorities in the region, specifically the Volcanic Ash Advisory Center in Darwin, have been issuing repeated warnings throughout this eruption about ash plumes reaching flight-relevant altitudes, forcing airlines to reroute around a hazard that didn't exist on any chart 3 months ago. And Titan Ridge is far from the only submarine system in this part of the world, capable of turning dangerous with almost no notice. Down in the Solomon Islands, a volcano called Kavachi has spent decades building itself up from the seafloor in repeated bursts, occasionally breaching the surface as a temporary island before collapsing back beneath the waves, and it's infamous enough among marine biologists for having sharks recorded swimming inside its crater between eruptions. Further east, in the Caribbean, a submarine volcano called Kikum Geni sits close enough to Grenada that authorities maintain an exclusion zone around it at all times, precisely because nobody wants to be caught on the surface if it goes. The pattern across all of these systems is the same. Shallow submarine volcanoes are disproportionately dangerous compared to their land-based cousins, not because they're necessarily larger, but because the interaction between magma and seawater multiplies the explosive potential, and because almost none of them get the continuous monitoring that a populated land volcano would receive. Titan Ridge simply happens to be the newest name added to that list, and quite possibly the least expected. There's another possibility hanging over this entire event that genuinely has volcanologists excited in a way you don't often see in this field, and that's the question of whether Titan Ridge is going to give birth to an actual new island. This isn't science fiction. It has happened before and recently. Home Reef in Tonga produced a temporary island in 2006, and again in later years. Surtsey, off the coast of Iceland, emerged from the sea in the 1960s and became one of the most studied pieces of new land on Earth precisely because scientists got to watch, in real time, how bare volcanic rock gets colonized by the first traces of life. Pumice rafts themselves play a strange, almost protective role in this process. As they pile up around an erupting vent, they can act like a natural shield, insulating the fragile new material building up beneath the surface and, in some cases, allowing genuinely new land to accumulate and persist rather than simply washing away. NASA's chief scientist overseeing this monitoring effort put it about as plainly as a scientist ever does, saying they were eagerly watching to see if a new island was about to be born, something satellites have only rarely been able to observe as it actually happens. Whether Titan Ridge ultimately breaches the surface and holds, or simply builds up and slumps back down into the sea the way most submarine eruptions eventually do, this is one of the only times in human history that we've had this kind of continuous orbital eyewitness to the entire process, from the very first tremor onward. There's actually a reasonably well-documented pattern for how these ephemeral islands tend to behave once they do emerge. And it helps explain why scientists are so cautious about declaring victory, even if Titan Ridge eventually pokes above the waterline. Loose volcanic ash and pumice, freshly deposited and completely uncemented, erode astonishingly fast once ocean waves start working on them directly. Some temporary islands born from shallow eruptions elsewhere in the Pacific have lasted only a matter of weeks before wave action ground them back down below sea level, essentially undoing in a month what the eruption spent building over days. Others, particularly when the erupted material includes enough solid lava rather than just loose ash and pumice, have managed to harden and persist for years, occasionally even decades, before erosion finally wins out. Which outcome Titan Ridge produces, if it produces one at all, will likely depend on exactly how much of what's coming out of that vent is fine, crumbly pumice versus denser, more resistant lava, something researchers are still trying to determine from a distance because nobody has been able to safely approach the active vent itself to take direct samples. Now, while all of this has been unfolding as a fascinating scientific spectacle from orbit, it has not been abstract or harmless for the people who actually live near it. The communities on Manus Island and across the wider Admiralty Islands group have spent the last several months dealing with the very physical consequences of an eruption happening less than 130 kilometers from their coastline. Starting in early June, those pumice rafts we talked about, the ones spanning tens of square kilometers, began drifting northwest with the currents and slamming directly into island coastlines. Local residents described entire stretches of shoreline choked with floating rock, boat channels clogged to the point where fishing vessels simply couldn't get through, and beaches transformed overnight into fields of gray, porous stone. This isn't a cosmetic inconvenience either. Marine researchers who have studied pumice events like this elsewhere in the Pacific including a comparable event that reached Japan's coastline back in 2021, documented real ecological damage, pumice blocking sunlight from reaching seagrass beds and coral below, filter feeding fish in aquaculture cages dying after ingesting the material, and physical damage to reef structures from the sheer volume of rock grinding against them in the surf. For fishing communities whose entire livelihood depends on clean water and healthy reefs, a floating gray continent showing up on their doorstep is not a curiosity. It's a direct economic and ecological hit that could take years to fully recover from. Local news coverage out of Papua New Guinea in early June described the situation along parts of the Manus coastline bluntly as a disaster, with fishermen unable to launch boats through channels packed solid with floating rock, and residents reporting that the smell of sulfur carried on the wind for days at a time whenever the plume shifted on shore. Even months later, after the main rafts broke apart and scattered across the wider ocean, patches of pumice were still turning up in sheltered coves and along quieter stretches of beach, a lingering physical reminder of an eruption that, for the people living closest to it, never really felt like a distant scientific curiosity in the first place. And there's a layer to this story that makes it even more haunting once you know it. The people of Manus Island have their own oral history connected to this exact stretch of ocean, long before any satellite ever photographed it. Local tradition holds that the ancestral home of the Titan people, the group whose name was eventually given informally to this newly erupting ridge, was itself devastated and reduced down to what's now called Circular Reef, roughly 40 kilometers away, following some uncertain natural catastrophe generations ago. The survivors drifted, resettled, and their descendants today live mainly along the southern coast of Manus Island. Whether or not that ancestral disaster was volcanic in nature is something science can't fully confirm, but the symmetry is hard to ignore. A community whose own origin story includes losing an island to the sea is now watching, from the shore, as the ocean directly behind them starts building something new, or possibly destroying something old, in exactly the same restless patch of water their ancestors once called home. This brings us to the part of this story that I think deserves far more attention than it currently gets, because the Bismarck Sea has already demonstrated, within recorded history, exactly how catastrophic volcanic activity in this basin can become. In March of 1888, a volcanic island called Ritter Island, sitting in the same general stretch of sea off the coast of what was then Papua New Guinea, underwent a sudden and massive structural collapse. A huge section of the volcano's flank, estimated at somewhere around 5 cubic kilometers of rock, simply gave way and slid into the ocean in a single catastrophic event known as a sector collapse. The displacement of that much material happening almost instantly generated a tsunami that slammed into surrounding coastlines, with waves reported in the range of 10 to 15 meters high in places. The death toll, based on historical estimates, ran somewhere between 1,500 and 3,000 people. It remains one of the largest volcanic sector collapses recorded anywhere on Earth in modern history, and it happened in this exact ocean basin, driven by the exact same underlying tectonic chaos that's currently feeding Titan Ridge. What makes the Ritter Island disaster especially unsettling in hindsight is how little warning it gave either. Contemporary accounts from the late 19th century describe minor volcanic activity in the days beforehand, nothing that suggested an entire flank of the island was about to detach and slide into the sea. Coastal villages along New Guinea and the surrounding islands had no meaningful warning system, no time to move to higher ground, and the wave that followed reportedly struck within minutes of the collapse itself, arriving faster than anyone could realistically outrun. That event should serve as the honest, sobering counterweight to all the fascinating imagery coming out of this new eruption. This region has already proven, in living geological memory, that it is capable of producing sudden, catastrophic, life-taking events, not just slow curiosities that scientists get to observe patiently from orbit. So where does that leave the actual risk assessment for what's happening right now? In the immediate aftermath of the eruption's onset back in May, authorities did raise concerns about localized tsunami risk, given how shallow the eruption appeared to be and how quickly the situation was evolving with almost no baseline data to compare it against. As the weeks went on, though, the picture became somewhat calmer, at least in terms of the immediate explosive intensity. By late May into early June, monitoring from the Rabaul Volcano Observatory showed periods where the eruption's hydroacoustic signals, essentially the underwater sound signature produced by ongoing volcanic activity, would decrease for a few days and then surge back up again, a stuttering, inconsistent rhythm rather than one smooth decline. Thermal anomalies around the vent area actually intensified during some of these quieter acoustic periods, which told scientists that reduced noise didn't necessarily mean reduced heat or reduced magma supply, just a change in how that energy was being released. Through most of June, the eruption plume was still capable of rising several kilometers into the atmosphere on its more active days, still producing new pumice, still discoloring water across wide stretches of the surrounding sea. Then, moving into July, the data finally started showing a real, sustained decline. Reports covering the period from roughly the middle of June through early July described the eruption dropping to what observers called very low levels. No new seismic activity had been detected for more than a month by that point, and the number of daily hydroacoustic signals, which had been in the hundreds during the most intense phase back in May, had fallen to fewer than 10 per day. The pumice rafts that had been choking the coastlines of the Admiralty Islands had largely broken apart and dispersed across the wider ocean, though patches of it were still washing up on beaches and lingering in sheltered coves. A minor plume of discolored water was still visible drifting south and southwest of the site, and observers occasionally caught a single discrete puff of steam rising and dissipating within a few kilometers, but the dramatic, sustained multi-kilometer eruption columns of May and early June had essentially stopped. Here's the honest, important caveat that any serious volcanologist working on this event would tell you directly, and it's the same caveat that applies to almost every unmapped, poorly instrumented volcanic system on the planet. A lull is not necessarily an ending. This entire eruption began with two separate precursor earthquake swarms weeks apart, in March and again in April, before the actual eruption broke out in May. There is no dedicated seafloor monitoring network sitting on top of Titan Ridge, the way there would be for a well-studied land volcano. Everything scientists know about the current state of the system comes from distant seismic stations, passing satellites, and the occasional hydroacoustic signal picked up by hydrophones, built for entirely different purposes. If magma supply from depth hasn't actually stopped, if it has simply paused or shifted pathway, or started slowly building pressure again beneath a partially sealed vent the same way a system can behind rock and mineral deposits on land, there is genuinely no guarantee anyone would see it coming with much lead time. The system could stay quiet for months. It could also flare back up with a fresh earthquake swarm at almost any point, the exact same way the first two swarms in March and April gave almost no warning before May's full eruption arrived. It's also worth putting this event into the wider context of what else has been stirring across the planet's volcanic systems during the same stretch of months, because Titan Ridge has not been erupting in isolation. Weekly global monitoring reports covering the same period this year logged ongoing activity at more than 20 other volcanoes simultaneously, spanning from Kilauea in the United States to Shevelush in Russia, Semeru and Merapi in Indonesia, Mayon in the Philippines, and Etna in Italy, which itself saw a new fissure open between two of its summit craters during the same window Titan Ridge was tapering off. None of that is necessarily connected in any deep causal sense. The planet's volcanic systems don't operate on some unified schedule, sharing no direct plumbing and no synchronized triggers, and having 20-plus active volcanoes at once is closer to a normal baseline than an anomaly. But it's a useful reminder that Earth's crust is never actually still. There's always pressure building somewhere, always a fault creeping, always magma finding the path of least resistance, somewhere beneath an ocean or a mountain range. Titan Ridge simply happened to pick one of the least watched, least mapped corners of that entire system to make its presence known. And that alone tells you something important about how much of this planet's active geology is still essentially invisible to us until the moment it erupts. So, stepping back and looking at the complete picture, what are we actually left with here? A previously unknown volcanic feature, sitting at the collision point of a transform fault and a spreading ridge in one of the most tectonically scrambled stretches of ocean on Earth, produced two precursor earthquake swarms over the course of a month, then erupted violently enough to discolor nearly 3,000 square kilometers of open ocean, generate pumice rafts larger than entire islands, threaten regional aviation, damage coastal ecosystems, disrupt fishing communities with deep ancestral ties to this exact water, and raise a genuine, still unresolved scientific question about whether a new piece of land is being born in real time. It did all of this in a location that sits inside a sea already responsible for one of the deadliest volcanic tsunami disasters in recorded history. And as of the most recent monitoring available, the eruption has quieted dramatically. But the underlying tectonic conditions that produced it in the first place, the sliding fault, the spreading ridge, the thin, fractured crust letting magma punch upward with unusual ease, have not gone anywhere at all. They're still sitting right there, beneath water that most maps still can't accurately describe. What happens next genuinely is an open question, and that's not a cop-out answer. That's the honest state of the science right now. If seismic monitoring picks up a fresh swarm the way it did in March and April, that will be the signal that this system is recharging and could erupt again, possibly even more intensely than the initial event, especially if a genuine island platform has been quietly building beneath the waves during the quiet phase. If the seismicity and hydroacoustic signals stay flat for months on end, scientists will treat that as evidence the immediate magma supply driving this specific episode has likely exhausted itself, at least for now, even though the deeper tectonic plumbing feeding it will remain fully intact for the next eruption, whenever that comes. Either way, satellites are going to keep watching this exact patch of ocean far more closely than they ever did before May 8th. simply because this event proved, in the most dramatic way possible, that there are still genuine blank spots on this planet capable of producing something this significant with almost no warning at all. If you found this as wild as I did putting it together, do me a favor and drop a like on this video. It genuinely helps push content like this out to more people who'd find it just as fascinating. Let me know in the comments what you think is actually happening under there, whether you think we're watching the birth of a new island in real time, or whether you think this is the opening chapter of something much bigger still building beneath the surface. And if you want to stay updated as new satellite passes and monitoring reports come in on this, make sure you're subscribed and sharing this with anyone you know who's into geology, natural disasters, or just genuinely strange under-the-radar science stories. Because this is exactly the kind of event that tends to get forgotten the moment the news cycle moves on, right up until the moment it isn't forgettable anymore. The Bismarck Sea has already shown us once, in 1888, exactly how violent this stretch of ocean can become. Right now it's quiet. But underneath that quiet is one of the most structurally chaotic, fault-riddled, and least understood pieces of seafloor on the entire planet. And something down there has already proven, this year, that it's very much awake.